Okay, so chapter 25 kind of goes along with chapter 4 because chapter 4 was all about the atom and we talked about the parts of the atom, right? We talked about the protons and neutrons being in the nucleus and the electrons being around the outside of that. But one thing that we did not talk about is that the nucleus, which has the protons and neutrons, right? What holds all that together? There's some energy that has to hold the protons and neutrons together in that nucleus. And if that energy is off just by a little bit, if you have the wrong number of protons and neutrons in the nucleus, that nucleus falls apart. And so one thing that we need to talk about is this idea of radioactive decay. Okay? So, we know that some nuclei are unstable because they have the wrong ratio of neutrons to protons. Right? For the lighter elements, for the elements near the top of the periodic table, it's like a 1-to-1 ratio of neutrons to protons. As you get past about element 20, it goes to about a 1.5-to-1 ratio of neutrons to protons. But you don't need to really know the ratios. The idea is that every single element has a series of isotopes, and some of those isotopes are unstable. Their nuclei do not stay together. They fall apart. Okay? And so that extra energy that builds up and must be relieved gets relieved by emitting radioactive particles. Okay? Because we know in nature, everything in the universe is trying to be at the lowest energy possible. If there's too much energy in the nucleus of an atom, that atom's nucleus is going to fall apart. So, what kind of radioactive particles are possible to come out of a nucleus of an atom? Well, one of them is called an alpha particle. An alpha particle is essentially the nucleus of a helium atom. Now, we know helium atoms, and we can see here, helium atom has 2 protons. It has a mass number of 4, and 4 minus 2 tells you there must be 2 neutrons also. So it has 2 protons, it has 2 neutrons, and that's what an alpha particle is. It's 2 protons and 2 neutrons. So sometimes an unstable nuclei can emit an alpha particle, which means basically it's spitting out 2 protons and 2 neutrons out of its nucleus. Now, since we're not talking about the electrons, technically, we're talking about a helium nucleus without its 2 electrons, but since we're only talking about the nucleus and we're not worried about the electrons, we don't usually worry about the charges. Okay. Another radioactive particle that's possible is called the beta particle. A beta particle is essentially an electron. Now, I know what you're thinking. You're thinking, wait a minute. You just said that the electrons were not part of this discussion because electrons aren't in the nucleus. But technically they are. Right? One thing that we know about protons and neutrons, and let me put this up here real quick. One thing that we know about protons and neutrons is that they're almost the same size, right? If you look at the size of a proton, here's my proton, and we look at the size of a neutron, here's my neutron, they're almost the same size, right? We usually say that a proton weighs 1 AMU and the neutron weighs 1 AMU. But that's actually not true. A proton is not exactly 1 AMU. It's a little off of that. And a neutron is also a little off of that, but just a little bit more. It's just a tiny bit heavier. Why is a neutron heavier than a proton? And that's actually because a neutron is actually a proton with an electron stuck to it. If you take a proton, which is positive, and you stick an electron, which is negative, on it, the positive and negative are going to cancel each other. You're going to end up with a neutral particle. And that particle is going to be the same size as a proton, except that it's going to have a tiny bit more on it because it has an electron. So, what happens when a beta particle, is what we call this, a beta particle comes out of a nucleus? Well, essentially, you're spitting the electron off of one of your neutrons, and the neutron turns back into a proton. Okay? So it is possible to release an electron out of a nucleus because the electron comes out of a neutron. Right? And then we have a gamma ray. A gamma ray is the third type that we're going to talk about in here. It's not the only three, but these are the three most common radioactive particles. A gamma ray is just energy. Okay? It doesn't have any mass. So you can see that when we write it as a nuclear symbol, like we're doing here, you notice that we don't write any charge or any mass, because it's just energy. Okay? Gamma ray is energy. So the three most common radioactive particles that can be spit out of an unstable nucleus is an alpha particle, which is 2 protons and 2 neutrons. We write it like this. A beta particle, which is essentially an electron and can be written either one of these ways. Or a gamma ray, which is just energy. And this is the way we would write it. So if we wanted to write out what we call a nuclear equation, this would show the radioactive decay of an isotope. Now you're going to need a periodic table. You're going to need to be looking at your periodic table as we do this. It's going to make a lot more sense if you do that. So here's our example. Let's say that we wanted to write out the nuclear equation for the alpha decay of radium-226. Okay? Alpha decay of radium-226. Now, I know a few things from this. Okay? I know, first of all, that it's asking me to take an alpha particle out of radium-226. It's decay, so that means the alpha particle is being released out of it. It's not going into it. Okay? So I'm going to start by writing out my isotope that is radioactive. That's the radium-226. So I need to look on the periodic table. I need to look up what the symbol for radium is. And then we're going to put 226 after it. So radium. We have 226 is the mass number. Right? And then we have to fill in the atomic number. The atomic number is 88. Now we have this isotope that has a mass number of 226, has an atomic number of 88. And now we're going to show that it's going to change. So we're going to draw our arrow to show that there's going to be a change that happens. And we know that one of the products of this change is an alpha particle. Well, we learned earlier that an alpha particle is written as 4,2He, so we're going to write 4,2He. That's one of my products. But what's the other product? In other words, what happens to radium once it releases 2 protons and 2 neutrons? Well, we can figure this out by doing some really simple math. We know that the mass of radium-226 to start was 226. It released a mass of 4 from the alpha particle. What's left? Must be 222. If radium originally had 88 protons, and it released 2 of them, how many are left? Must be 86. What's element 86 on the periodic table? Take a moment to find that on your periodic table for me. Did you find 86? It is radon, all right? Radon, which is Rn. So, if I were to ask you to write out a nuclear equation of something going through a decay, right? This is how you would go through the process. What if I had asked you about the beta decay of radium-226 instead, right? How would that look instead? Well, I would still start off with radium-226. But since it's going through beta decay, right, then I'm going to put a beta particle here first. And then I'm going to go through the same math steps that I did before. If I started with a mass of 226, then my mass better be the same on this side. What's the mass of a beta particle? 0. So how much mass is left in my extra particle, my extra isotope? Still must be 226, right? 226 plus 0 has to equal 226. The bottom number, which is the atomic number, started off as 88. I have gotten rid of -1. So what do you have to add to -1 to get 88? Well, wouldn't that be 89, right? 89 plus -1 gives you 88. What's number 89 on the periodic table? That would be actinium. AC. Okay? So this is what we mean by writing out a nuclear equation. We can show, as long as somebody tells us what the decay is, we can show what's happening in an equation like this. Okay? All right. Let's get past that. Next thing that we need to understand about this splitting, this decay of a nucleus, is that it takes some amount of time for this to happen. The time that it takes for half of the isotope to decay into another isotope is called the half-life. Okay, so half-life is an amount of time. For instance, the half-life, and we abbreviate half-life as this T1/2, the half-life of uranium-238, which is a radioactive isotope of uranium, the half-life of uranium-238 is about 4.5 billion years. So that means if you had a sample of uranium-238 in 4.5 billion years, only half of that sample would still be uranium-238. The other half of it would have decayed into something else. So if we do the little exercise with this, if I started off with a rock that was 100% uranium-238, in 4.5 billion years, I'd be left with 50% of uranium-238 left in that sample. What happened to the other 50%? It turned into something else. Now, let's just say that I was able to live a really long time, and I could wait around another 4.5 billion years. What would be left in that rock? Well, I started off with 50% uranium-238, half of that, right? Half-life means I'm always taking half of what I started with. Half of 50% is now 25%. If I waited another 4.5 billion years, I would take half of 25%. So notice I didn't go from 100 to 50 and 50 to 0. That's not how this works. I always take half of what's left. That's how a half-life works. Now, one of the really useful radioactive isotopes that is out there is actually carbon-14. Okay? Carbon has many isotopes, carbon-12, carbon-13, carbon-14, right? And it turns out that since you and I and most living things on Earth are made out of a lot of carbon, we contain many different versions of carbon in our body. You're made up of mostly carbon-12, but you do have some carbon-13s and carbon-14s in your body, which, carbon-14, by the way, is radioactive. Yes, you are radioactive, and so are all other living things. After about 5,730 years, the carbon-14 in a living thing will turn into nitrogen-14. But you can only witness this happen as soon as the item dies, okay? So if we wanted to take a living organism and we wanted to find out how old it was based on its carbon-14 content, it wouldn't work because you constantly replenish the carbon in your body because you constantly eat, and so do all other living things. But once the living thing dies, it stops eating, and the amount of carbon-14 in its body is now going to decay and not be replenished. So let's just say just for fun here, just for numbers to use. It's not really how much carbon-14 you would have in your body. But let's say that we have an organism that has 10% carbon-14 in its body. It's dead. and now we wait 5,730 years. How much carbon-14 would be left in the body? Now 5%. If we waited another 5,730 years, we would only have 2.5% carbon-14. So you notice how this could be useful. If you could measure how much carbon-14 is in the bones or in the little bit of fossil that's left from some kind of organism, you could figure out how long ago it died. Now, you could see that we would eventually run really, really low on the carbon-14, and so carbon-14 carbon dating is usually only good up to about 50,000 years old. Right? So it's not like we could date the dinosaurs using carbon-14. We would have to use some other radioactive isotope in a living thing besides carbon-14. Okay? And then the last thing that we need to understand about nuclear decay, radioactive decay, is that we can actually use it for things. Right? There's two different ways that nuclear reactions happen. There's either nuclear fission, which is when the nucleus actually breaks apart, and there's nuclear fusion, which is where you could actually take particles and put them back together to make a nucleus. Let's talk about fission first. Fission is the splitting of an atomic nucleus. Okay? We can do that, right? If we take, let's say, a really big nucleus that's unstable, like uranium-235, and we were to, shoot neutrons at it, and one of the neutrons hits this very unstable nucleus, and instead of having to wait 4.5 billion years, it immediately causes it to split. There's some energy that we get out of that. In fact, this is how a nuclear power plant works. It's also how a nuclear bomb works, right? The same process happens. We're splitting the nucleus that was going to split anyways eventually, but we're causing it to speed up by bombarding it with some particles to cause it to split sooner. And we release all of that energy all at once. Okay? There's a lot of energy that's in that. But even more energy comes out of nuclear fusion. Fusion is if we take two smaller atoms, right, and we combine them to form a larger atom. So this happens in the sun, for instance. The sun has these hydrogens, these really tiny nuclei, and it forces them to come together. And when they come together to form a helium nucleus, a whole bunch of energy, way more energy that's in fission, is released. Now, we haven't found a good way of doing this here on Earth yet. When we do, we'll solve the energy crisis that we might have here. But for now, we have to kind of rely on nuclear fission for our nuclear power plants. Okay? So that's chapter 25 sort of in a nutshell. That's the basics of what you need to know out of that chapter.